In our previous lecture, we have seen the Wagner-Merwin rearrangement and the Pinnacle rearrangement. In this lecture, we are going to see another three simple carbocation rearrangements involving carbocations. The first one we are going to see is Dienone-phenol rearrangement. So this compound is called dienone because it's having ketone and there are two double bonds. So it is called dienone. Dienones in presence of acid or sunlight, it's converted to a phenol. You can see that here the two alkyl groups are in the same carbon atom, but instead in the product, it is found that this alkyl group is migrating to the adjacent center. So it is called a dienone and it's a phenol. So this rearrangement is called dienone-phenol rearrangement. This is another example in which we have got this again a dienone, and these are the two alkyl groups attached to the carbonate system. It's also in presence of an acid or in presence of sunlight. The alkyl group migrates to the adjacent possible position, and this one alkyl group migrates to this position, and this phenol is formed. Okay, this phenol is formed. You can see that this can migrate to the adjacent position or to this position, depending upon the nature. If you want to know more about this, you may refer to the book exactly. The book name is Name Reactions. I have the book with me as a personal copy. I don't know whether its soft copy is available or not. Okay, you can refer to page number 176 to 178. You can get this rearrangement, dienone-phenol rearrangement. Now let us see the mechanism of process. We are going to see the proposed mechanism. We are going to see the proposed mechanism of the process. And this is actually a dienone. You can see that this carbon is having a hydrogen atom. Hydrogen, H plus will add. You know that there are two lone pairs in the oxygen atom. Lone pair adds to H plus and it forms a protonated dienone. The oxygen is having positive charge, hence what happens is that this bond shifts towards the oxygen atom, causing a positive charge in this carbon atom. To this double bond migrates, resulting a carbocation here. You can see that it is actually a secondary carbocation. We know always the tertiary carbocation is more stable. Hence, what happens is that this second alkyl group migrates to this carbon atom by methyl shift. It's called the 1,2-methyl shift, by 1,2-methyl shift, resulting this carbocation. This is actually a tertiary carbocation. Later, what happens is that there is a alpha hydrogen over to the carbocation. This hydrogen deprotonates and it gives you phenol. So this is the simple mechanism of the dienone-phenol rearrangement. This is the mechanism of dienone-phenol rearrangement. So it involves a secondary carbocation first. Later, the secondary carbocation rearranges to form a tertiary carbocation. In this case, also there will be a carbocation here. And can you just go through this mechanism and see the products? See, this is the self-study problem. Can you try how you get these two products? See what would be the possible reason for that. So here also, what happens is that if you want, I can give a hint for this. In presence of proton, it forms a protonated ketone like this. And you know, this double bond shifts here, and this bond shift towards the oxygen atom. That leads to OH here, That leads to bond shifts here, double bond is happening here, plus charge is here, and there is double bond here, there is R and R. There will be again shifting by resonance. There will be positive charge here. Then the alkyl group migrates here and gives a reaction. So what would be the reason for having the alkyl group out here? You can see that in the first step again, what happens is that we can also imagine like this. This is the OH plus charge is the oxygen atom. There's a bond like this. This bond can shift to this place, and that leads to the formation of a plus charge over here in the carbocation. So here there's a carbocation, and this carbocation can also facilitate the rearrangement. That's why we get this product also. So even though this product is a minor product, it's formed. Let us see another example for this reaction. You can see that in this reaction, this is a dienone. It's a dienone molecule. So there is C2H5. It's actually an ethyl molecule. So first step is protonation. It's a protonation step. Second step, there's a possibility here to shift here, but here the shifting is not taking place because there is no carbocation rearrangement possible. But here we can see that this shift will take place, and this carbon atom gets, when this shift is taking place, this carbon atom gets a positive charge. To this positive charge, this ethyl group is migrating to ethyl shift. And later it forms this compound. Later this compound, they can rearrange to form this compound. Hope that is very clear to you how to do this reaction. Okay, so we are expecting some unexpected. We are not expecting actually this product here, but we get an unexpected product here. We can shift the alkyl group from their respective positions. Another example is the rearrangement that's observed in santonin. Santonin is this compound. It's an analogous of the above compound. You can see that here there will be a possibility of migration here. So in presence of H plus, it gets a protonated alcohol. What happens here is that there will be shifting towards this side again. Again, what happens then after that, there is a plus charge in the center. This methyl group migrates and forms this product. It is called desmoproposantonin. The compound is called desmoproposantonin. It is the other reaction that involves the migration of carbocation. So you can see that here in this example, a diketone, dienone is becoming actually a phenol. So it's a very simple reaction. So there's migration of a methyl group here. We generally do not expect the migration of the ethyl group because the bulky group, but still this reaction causes the migration of the methyl groups also. So I would like to give you a few worked examples also. You can see this reaction here. This compound is converted to in presence of acid. Can you tell me how the reaction is taking place? So that we can make the numbering of carbon atom 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The numbering of the carbon atoms that you can employ. So you can see that in presence of H plus, there is deprotonation, and this migrates, the electron migrates. So I would like to represent the reaction like this. OH plus, there is here, here this bond migrates here and this bond migrates here. So there will be double bond here, there will be OH, positive charges here. Now there's a secondary carbon cation. This bond, sigma bond, migrates to this place, leading to the formation of OH here. And you can see that here, this is the fourth carbon atom, the 10th carbon atom, the 10th carbon atom, 9th carbon atom, 8th carbon atom, and 7th carbon atom. This is the 5th carbon atom. The 10 is here. We have got 9, we got 8, we got 7, 7, 8, 9. And the 7th carbon atom is bonded towards 5th carbon atom. 5th carbon atom. So this is the structure that we are getting. Now there is a possibility of deprotonation. There's a hydrogen over here. This will migrate here. And as a result of that, we'll be getting double bond here, like this here, and there's OH here, and there's a one like this. So another example of Dienone-phenol rearrangement. Now, in analogous example of the reaction, I would like to design the mechanism of this reaction. This CHR, the exocyclic double bond. Okay, so this compound on treatment with H plus, it is observed that this product is formed. The structure that CH2R is formed, and there's one methyl group here and another methyl group here. Can you design the mechanism of this reaction? You can see that here also the reaction proceeds in the same way. So there is H plus adds to this double bond. As a result of that, there will be CH2R and this carbon gets a positive charge. I'm just giving you hints only. CH2R, this carbon gets a positive charge. And the rest is same as that of the Dienone-phenol rearrangement. These are the applications of Dienone-phenol rearrangement. We can refer to more examples in the preferred textbooks. These are some of the applications. You may take down these applications and try to develop the mechanism of yourselves. They're very simple, and you can do that by self-study. When you prepare your lecture notes, kindly solve them also. So you can consider these 4 molecules as your homework. The second rearrangement today we are going to discuss is Demjanov rearrangement. Demjanov rearrangement is actually first reported in around 1903 by Demjanov. Actually, the name is not Demjanov. J is silent here. If you pronounce that as Demjanov or Demjanov. Okay. You can see that he is a Russian scientist. You can see the references cited here. The papers published around 120 years back. The journal is published in the Journal of Russian Physical Chemical Society and the Chemistry Centrium and the Russian Physical Chemical Society journals in the years 1903 and 1904. And this reaction is found to be of tremendous applications in organic synthesis. So this is actually involving cyclic systems, and actually we could find expansion of the rings here. You could find expansion of the rings here. Sometimes also contraction of the ring also is observed, but still it can proceed by a simple expansion, and it proceeds by carbocation rearrangement. Generally, the reaction is of primary amines. Primary amines react with nitrous acid, HNO2, nitrous acid, and give some rearranged alcohols. You can see that here in this reaction, we can see it started with the cyclobutyl ring, but ended up with a cyclopentyl ring. So there is generally expansion of the rings that is taking place in the Demjanov reaction. Actually, we expect the reaction like this. Generally, this is the expected reaction or by general mechanism. Okay, so this is the cyclobutyl methylamine. Compound name is cyclobutyl. It's actually methylamine. In fact, one methyl is substituted cyclobutyl group, one H is substituted cyclobutyl group. It is called cyclobutyl methylamine or cyclobutyl methanamine. This is the nitrous acid. Nitrous acid, you know that nitrous acid under the diazotization, and will give you a diazo compound. This compound, you know, what we expect is that we expect SN2 substitution, like the O lone pair in the oxygen atom is a nucleophilic system. Lone pair gives to the N2 and forms a ipso substitution. That means the same carbon atom substitutes, and it gives you the OH2 here, and it can go deprotonation to give alcohol. It's actually what we expect over here. But actually in Demjanov reaction, what happens is that this is the nitrated water. See, these are same. Till here, the reaction is same. Diazotization is happening. But you can see after diazotization, this goes out. This goes out. N2 goes out. And you know, to trigger off the removal of N2, there's an adjacent carbon-carbon single bond. This sigma bond is broken, and this sigma bond shifts towards this carbon atom. It's a carbon atom here. So if it is 1, 2, 3, 4, 5 here, you know, there's a new bond, the bond to 1 and 4 breaks, and a new bond is formed between the 4th carbon atom and the 5th carbon atom. So 4th carbon atom and 5th carbon atom. This is the 5th carbon atom. Sorry, this is the 1st carbon atom, because the bond is breaking and positive charge comes in the 1st carbon atom. 1st carbon atom, it will be the 5th carbon atom, it will be the 4th one, the 3rd one, and the 2nd one. Later, this carbocation is taken by the water. It gives a protonated alcohol that undergo deprotonation to give the cyclohexanol. Okay, so it's an alicyclic alcohol. It's an aliphatic alcohol. It's an aliphatic alcohol, but it's an alicyclic alcohol because OH is in the basic ring or skeleton. Okay, and it is later in 1935, Tiffeneau-Demjanov Rearrangement. Okay, they are French scientists, And actually, they were able to convert one amino methyl cyclohexanol, and they found that they're converting very fastly to cycloheptanol. Okay, and they suggested a different mechanism for this, and they found that their mechanism is similar to that of the reaction of Wallach. There's a reaction called Wallach rearrangement. They suggested that the reaction is similar to Wallach rearrangement. But later, scientists found that it is not the Wallach rearrangement, and they found that it's actually nothing but the Demjanov rearrangement. Okay, so then onwards, the reaction, that means the reaction of one amino methyl cyclohexanol to cyclopentanol. We are going to see in detail later, and this reaction is found to be the Tiffeneau-Demjanov rearrangement, or the TDR. Tiffeneau-Demjanov rearrangement, TDR. So here we can see that here we can expand the rings. That's the main striking point of the reaction. We could we could design the reactions that could give you the expansion of the ring. That's the main note of this reaction. So this is the reference for that. In 1937, the reaction is reported. This is the original reference for the reaction in 1930. It is suggested in the book Compton's Renders. We're going to see the mechanism of the reaction and the representativeness of the reaction. So here the reaction, Tiffeneau-Demjanov rearrangement, is actually the conversion of these compounds, amino methyl cycloalkanol. So amino methyl cycloalkanols to expanded ketones. It's called Tiffeneau-Demjanov rearrangement. The reaction involves some of the these reactions involves almost the same steps that of the Demjanov reaction. Only thing is that the substrate is different. Earlier we have used a primary amines. Here, not the primary amine is not the substrate, but here who is the substrate? The amino methyl cyclohexanol. This amino group, amino methyl, CH3 is NH2. Then this amino methyl. But this CH3, 1H is replaced by earlier a cyclohexane, but here it is cyclohexanol. It involves several steps actually. The first step is the formation of the nitrosonium ion. It's a very simple step that you know. Nitrosonium ion is formed. Nitrosonium ion reacts for N2O5, that is the reactant here. This will be taking the amino group, one proton of amino group, and it forms this system. N double bond to NH is formed. And you can see that here the water, we have got acidified water here. Acidified water is here, and the acidified water, it takes adds to the proton, and as a result of that, there will be protonation and deprotonation. As a result of that, there will be removal of N2. There will be removal of N2 taking place. So just like that of the Demjanov reaction, for the removal of N2, here what we use is that here there is an expansion, which is 1, 2, 3, 4, 5, 6, and 7. The 1, 2, 6 bond is breaking, and the sigma bond adds towards 7th carbon atom. So here we got 1, 2, 3, 4, 5, 6. Okay, 6, 1 bond was there, and that bond is broken, and that bond adds to the 7th carbon atom, the 7th carbon atom. Later, it forms a system like this. Later, it undergo deprotonation in presence of water. So you can see the OH bond is there. This bond shift towards here, and this is formed. Up to here, the mechanism is almost same, but here only it differs from that of the Demjanov reaction. Even then, the reaction is almost same. The first reaction steps are actually very common. Only thing is that earlier we use here a cyclohexane was the ring, but here we got a cyclohexanol as a ring, and there is OH here, and the OH under deprotonation and do the reaction. You can see that here also the N2 is there. Here is SN2 reaction. You can again see, you can see OH2 is there, there is protonated alcohol. Here we have got a protonated alcohol. H2O plus is here in this alcohol, but here we have got a not, we don't get a protonated alcohol as the in the penultimate step, but here we get a system like this, and to this the H plus gives off and give the product. So the reaction happens in 4 steps: formation of nitrosonium ion, nucleophilic attack on nitrosonium ion, then rearrangement, and remote N2 with alkyl shift. Actually, the reaction steps are almost same as the Dienone reaction. So this is the mechanistic view of the reaction, that this reaction. Is another example. This is cyclohexyl. This is a methylamine. It's a cyclopentyl alcohol is here. So this compound here also expansion of the ring and gives rise to cyclohexanol. The 4-membered ring, this compound will give you a 5-membered ring. It's actually a 6-membered ring. This will give you, it's actually, there should be a ketone over here. I forgot to add a ketone over here. Okay, so this is the mechanism of the first reaction. And you can see that the mechanism is almost, or not almost, it is exactly same as that of the previous reaction that we have seen. So this is a good example, another good example of the reaction. Here also, see the mechanism of generating of nitrosonium ion is different, but still the reaction is almost same. You can see the reaction. You can easily follow up the reaction, and you can see you'll be getting an expanded product. If you know the basic mechanism of the reaction, this can be easily followed up. So please go through this reaction also and try to solve this problem. The main agenda is to convert this compound. This is the reactant. Is a product. So we have seen that expanded ring over here. So that's all about the Tiffeneau-Demjanov rearrangement. Please do this question also. The last rearrangement we have to discuss in this unit is Fice rearrangement. Fice rearrangement is very common rearrangement. You might have studied that in your degree lectures also. It is nothing but the Lewis acid catalyzed rearrangement of a phenolic ester. This is a phenolic ester to a phenol with an ortho or para ketone. We can call that be ortho para hydroxy ketone. So the ester is modifying itself in presence of aluminum chloride to give ortho hydroxy ketone or the para hydroxy ketone. So reaction will happen in presence of anhydrous aluminum chloride. You can refer to any organic chemistry, simple organic chemistry textbooks for the reaction. The first step is actually, there is AlCl3, aluminum chloride. Aluminum chloride, AlCl3. You can see that here Al is aluminum is metallic center, Al 3%, Cl3 minus is here. This lone pair is electron rich. This lone pair donates to the aluminum and it forms an adduct like this. So there's actually a nucleophilic attack from the oxygen of the ester to the aluminum chloride, and that causes the formation of this new covalent bond between oxygen atom and aluminum, and it forms the system here like this. It's very common system. But you can see that the oxygen is having positive charge. Oxygen is electronegative element, it should not have the positive charge. So that leads to the formation of breaking of the bond and leads to the formation of acylium cation. So here this is this system, and you can see that here there is a formation of acylium cation. Like this it becomes, and the bond is actually breaks. This bond breaks, and this bond adds to this system, and it forms an acylium system. It forms an acylium system, and you can see that there is a new bond is formed between oxygen and the AlCl3. And this rearranges to form the acylium cation. This is the acylium cation. The third step is electrophilic attack. Okay, third step is electrophilic attack. This is the aluminated phenol. This is the acylium cation. This can proceed by ortho attack and para attack. The simple organic electrophilic substitution will take place. Aromatic electrophilic substitution will take place. So you can see that this double bond can donate to this carbon atom and form like this. Okay, and it will give you ortho hydroxy ketone in high temperature. But in low temperature, the para attack is more preferred. This oxygen adds to the para position, and this position is taken by the ketonic acylium cation and give you para hydroxy ketone. This is the basic mechanism of the Fries rearrangement. Actually, this Fries rearrangement can also happen through the photo reaction. So then we can call that the photo Fries rearrangement. I hope that you will study that in the unit photochemistry. These are some of the applications of the Fries rearrangement. This is actually our system. Is NHCO-CH3 in aluminum chloride. Here also similar. There is ester is an anilide, NH is an amide. That's all. The anilide, in fact, it's actually pyrimidine anilide, acetanilide. This compound, you can see that anhydrous aluminum chloride. This keto group rearranges to form the rearranges to the ortho position. The para position is already blocked, so para position is not involved, and you can see that you can get the reaction like this. Reaction process like this. There is a lone pair in the nitrogen atom. The lone pair will be a nitrogen atom, and also there will be a lone pair in the carbonyl system. Here also there will be a double bond O. There will be anhydrous AlCl3. It will be two lone pairs. Lone pair is added towards this aluminium and process the reaction. Please go through it and find whether you can finish the reaction or not. So this is another example of an ester is substituted by an amide and an amine. Instead of a CH3 or alkyl group, we have got an N secondary tertiary is actually in fact a tertiary amino system. NR2 is here. Dialkyl amino system is there. You can see that this system is breaking and will add to this ortho position or the para position. Similarly, here is another very important system. So you can see that this will break from this point will break from here and goes to this ortho position, this position. These are some of the applications of the Fries rearrangement. You may please go through this and refer and prepare your studies. Again, Fries rearrangement is not actually a difficult reaction to get now. This reaction is very simple reaction. It's found in many literature, many textbooks, and please go through this and find what that is. So, Fries rearrangement is actually nothing but a what we can say is that a Lewis acid catalyzed reaction. Remember that always we need actually a Lewis catalyst as a catalyst here. You see that most of these examples are taken from the book Gigerly, and you may try to explore that book, in fact. I can give you a simple more examples. I can see this example. You can try and enjoy yourself doing the reactions. So you can see that all these reactions I'm taking from the book Gigerly. This OMe here. This O. Here. And the beta position that was here. Here we use zirconium chloride. And chlorobenzene is a solvent here. At about 160 degrees Celsius. For 3 hours, there will be around 63% yield of this compound. Try to explore the reaction. One thing you should understand is that this is actually an OMe. OMe is there is an ether group. So this actually is a Lewis acid. Lewis acid can also cause ether cleavage. You know that it happens, but we just don't need to worry about this mechanism. Just okay. I just want to tell you that there is no need to worry about that mechanism. Another example I can provide you is this example. A system of expanded OAC. This reaction happens in presence of bismuth triflate. Presence of toluene at 110 degrees Celsius. We got this product. So that's all about the reactions. Okay. So thank you very much.